So mainly two definitions we have to remember. One is a specific energy source and specific power source. So energy source means the source which is actually will be used for quite a longer period of time, and it will be continuously supplying quite a high energy for longer period of time. Whereas specific power source, it is like a batsman who comes, plays for 3 hours and scores 40 runs. So specific power sources only used whenever there is a very steep requirement of the energy. So whenever the vehicle is going through the slope or high steep, at that time specific power sources being used. So this definition we have seen already, that is specific energy. Specific energy is defined as the energy capacity per unit battery, watt hour per kg. So whatever is the weight of the battery, depending on that, the specific energy is calculated. So more is the weight, I think its specific energy capacity will reduce. So this is one very important thing we have to remember. That is best characteristic of the battery is it should be able to supply very high energy, but the battery weight should be as less as possible. So those kind of battery was very difficult to design previously, but in nowadays it is possible. So battery technology research related to battery, all these things are in very high demand. So any join this field of electrochemistry, you are very much welcome. Now, uh, hello,
Yes, sir.
is it audible? Okay. So what you can find here
Yes.
in this slide, this is actually a slide which was previously shown to you. Last day also have shown this slide. Again, I'll start from here only. So what it says is specific energy is defined as the energy capacity per unit battery weight, watt hour per kg. The theoretical specific energy is the maximum energy that can be generated per unit total mass of cell reactants. The energy in a battery cell can be expressed in Gibbs free energy. So all those things were expressed. This equation of specific energy theoretical. Okay, NFVR divided by 3.6 summation of Mi, where Mi is the sum of molecular weight of the individual specific things. So all these slides are old slide. So from the specific energy equation, it is clear that the highly electro negative element and a highly electropositive element, that is the reactants, both of low atomic weight produces ideal couple. So lower the atomic weight of the reactants or reagents, the overall weight of the battery will reduce. So hence the way we are saying lithium ion battery, why lithium ion, what is the speciality in that? So these are the questions can be asked in the interviews. So lithium ion both are actually very light, it's a very light couple. That means within a specific weight, you can pack much more reactants. Okay. So that's why lithium ion is a ideal couple. Hydrogen, lithium, or sodium would be the best choice for the negative reactants. So you are finding lithium ion means lithium will be a negative reactant. High and lighter halogens, oxygen, sulfur are the best choice for the positive elements. Okay, so any of these three things, and depending on the lithium characteristics, we can use any of these three things as the positive reactant. So lithium as negative reactant, because lithium is very light, we can pack much of this reactant inside the battery. So battery will last for longer time, it will be delivering energy for the longer time. So this is one of the main reason why lithium ion battery is so much in use. To put such couples together in a battery requires electrode designs for effective utilization of the contained active material, as well as electrolytes of high conductivity compatible with the materials in both electrodes. So all this discussion we had seen last day, but today what we are going to see is there is some discussion on the specific energy, and we are finding this table. So I will not be able to explain everything today, but you just see this table, because initially there was acidic aqueous solution. This is taken from the book of Ehsani, and you are finding that NiOOH. So there are a lot of alkaline aqueous solution battery likewise, and towards the end you are finding that lithium and carbon, Li and C. So LiCOO2, they are the candidate for the a new battery for EV and HEVs. And you can find out the specific energy. So specific energy watt hour per kg. So per kg watt hour should be more. Watt hour is watt into hour. That is, watt means nothing but joules per second. That means energy per time multiplied by time. That means you are actually finding energy. So energy per kg, energy per kg, that you are finding. What is the definition of a specific energy? It is nothing but energy per kg. And you are finding that this lithium LiCOO2, this is giving you quite a high specific energy watt hour per kg. It is almost 320. Okay, and there are actually higher contenders. Cl2Zn, this is giving you 833. There is another O2Al, they are giving you 2815. There is another FeS2LiAl, this is giving you 650. But there are other parameters because of which they are not selected for battery related applications in EV. And one of the very big constraint is thermal and heat management. Okay, so looking at all these things, lithium ion battery can be one of the very big contender for EV related battery. And what is the specific energy for that? That is watt hour per kg, that is 320. I'm just giving an example. If it is 5 kg battery, if it is a 5 kg weight battery, that means how much energy you will be getting from that? That is 320 into 5. That means around 1600 watt hour that you are going to get. So more than 30 different types of electrode couple have generated battery systems with reliable, high performance, inexpensive. Inexpensive is very important thing for EV. If the EV battery comes down, that will promote to a very higher extent. That we have to understand. So high power energy source for electrical traction. Traction means just to take the car forward. Theoretical specific energies of superior couples for EV, HEV are given in the table. So there's the table. You should know what can be the couples. So what can be the positive, what can be the negative of the battery. All those things you should know. So in case of organic lithium, LiCOO2 is the positive part and LiC is the negative part. So this is one of the thing which is making lithium ion battery. Practical specific energies, however, are well below the theoretical maximum. This discussion that what is meant by practical specific energy and what is meant by theoretical specific energy. So next slide will answer a lot of your questions. And next slide is very important. So apart from the electrode kinetic and other restrictions that serve to reduce the cell voltage and prevent full utilization of reactants, there is a need for construction material that add to the battery weight but are not involved in the energy producing reaction. Very important thing is the casing of the battery. So what they could not tell clearly, but they have indirectly given a hint. They have indirectly told that whatever are the material the casing is made of, that casing material should be as light as possible and as sturdy as possible, because casing material is increasing the kg, that is the weight of the battery, and casing materials, they are not taking part in the energy generation. So you cannot remove the electrode, you cannot remove the reactants, you cannot remove the electrolyte, because they have to be there, because they are the main energy generating element. But other things, that is casing, contacts and all those things, should be lightweight. So one very important thing, those who are thinking of future study, you always think of material science, because material science is a very important field of research. And as there will be a semiconductor boom, material science will be very sought after field. Now this slide I will ask you in the exam. So there is a possibility that this specific energy slide question will be asked in the exam. You can see here whatever is the total weight. So I told you that specific energy is directly is a function of what is the weight of the battery. You can find here in this round kind of a thing, there is a pie chart kind of a thing. The figure shows that about 26% of the total weight of the battery is directly involved in producing the electrical energy. Which are the 26% that we are going to see? The remainder is made up of. So here, this part at the top, I think you have to follow this thing, whatever cursor I'm showing. So this is PB plus PbO2 plus H2SO4. They are actually the energy generating material. So this is the 26%, nothing but the reactant. And remaining 1, 2, 3, 4, 5. So what is one potential cell reactant that are not discharged at the rates required for EV operation. That means they are also this one number, okay, pie chart, this pi, what you are finding is they are also reactant, but they are inactive reactant, because you cannot put all the reactants together at the same time for generating energy. So these are active reactants which are constituting 26% at the top, but these are inactive reactants. So they are actually working as a non-energy generating element. Second, you are finding water in electrolyte. Okay, water in electrolyte is required, but too much water in electrolyte, that water is not generating energy. Third is current collectors. So current collectors, they are grids. Actually, they are the, you can say, collecting material for the current, and they are actually not a energy generating element, but they're required. They're required. You cannot say that human body should be brain only. Okay, because brain is the most important part of human body, but the whole human body cannot be brain. To run the brain, other parts are also required. Exactly the same thing. Current collector, water, all these things are not directly energy generating element, but they are required. Without that, the energy generation cannot happen. Top lead. Okay, so whenever the battery is there, it is covered by some kind of plastic, very hard plastic material, that is top lead. Actually, this top lead is saving the inner parts of the battery. So somebody will say, sir, it is not required. We cannot say like that. Top lead is required. But we have to do material science related study, so that we have to find out which are the very lightest kind of plastic which can generate the top lead, and which will not reduce the specific energy. Because more is the weight, watt hour per kg value will reduce. And last thing is cover, container, and separators. So these two, 4 and 5, they are mainly the body, that is outside body, which we call as chassis. Third number is current collector, second number is water in electrolyte, and number one is un or non-reacting reactants. So this constitutes total 74%, and this 74% are non-energy generating element. But whenever I am saying a battery, at that time this 100% is considered in that watt hour per kg. In that kg, all these 100% are being considered. But in that, only 26% is generating energy, remaining are not. So that's why proper generation of battery, or proper selection of materials for battery, is very much important. So it is said here, potential cell reactants that are not discharged. Number two, water used in solvent for the electrolyte. Number three, lead grids for collection. Number four, top lead. And actually grids are made of lead, that is PB. Okay, and number five is cover, connector, separators. All these things are actually increasing the weight of the battery unnecessarily. I cannot say unnecessarily, but they are actually reducing the specific energy of the battery. So this pie chart is for weight distribution of the components of a lead acid EV battery with a specific energy of 45 watt hour per kg. Now, how much is the actual watt hour per kg? Actual watt hour per kg is 74% more than this 45. So if you divide this 45 with 0.74, 0.74 कहाँ से आ रहा है? Because this 26% is generating this 45 kilowatt. If this 70, if this remaining 74% was also reacting material, or if they were also generating energy, in that case the actual specific energy would have been 45 divided by 0.74, and that would have actually increased the energy, specific energy of the whole thing. Right. So the similar ratio of the practical to theoretical specific energy is expected for each of the candidate system listed in the table shown in the previous page. So whatever you are finding here in this slide, this is actual per kg. This is actually the theoretical watt hour per kg. Practical watt hour per kg will be 45 divided by 0.26, because 0.26 is the 26% element. Previously, I think I told it wrong. Divided by 0.74, it should be divided by 0.26. Right. So that will be the practical watt hour per kg. So theoretical and practical, whatever you are finding now here, 45 watt hour per kg, it is actually practical, but theoretical should be more than that. Now we are coming to a very important. So this was the discussion about specific energy. Now discussion about specific power. So specific power actually is so relation between energy and power. That is, energy per time is equal to power. This in a unit for the energy is joules, and unit for power is joules per second. So specific energy versus specific power. I told you that for EV, specific energy is the main consideration. because specific energy tells me that once I recharge the battery, how long it can go, because specific energy decides the range of the EV since it limits the vehicle range. So for specific energy, whenever I am saying EV requires high specific energy. For hybrid electric, specific power should be high, because hybrid electric means whenever I am going to use the second source, so fuel cell or EV, this gasoline and fuel cell can be one hybrid. Gasoline and battery can be another hybrid. So the hybrid source, that extra source apart from gasoline, is called as a bumper source. That bumper source is used only whenever we are requiring too much high power in a very short time. So high power in short time means we require a specific power source or a power source with high specific power. So you have to remember this. That is for specific energy, it is requirement, specific power, high specific power, it is HEV requirement. So because all the energy is form of energy source, engine or fuel cell, and sufficient power is needed to ensure the vehicle performance, mainly vehicle performance under a difficult situation. Hill climbing, regenerative braking, particularly during acceleration, all this time we need a specific high specific power source. Of course, other requirements should be fully considered in the vehicle drivetrain development. Specific power is defined as the maximum power of per unit battery weight that the battery can produce in a very short period. So this word is very important, that is in a short period. Short period means whenever I am defining specific power at the time is a very important parameter. Specific energy, time is not a very important parameter. In that case, weight of the battery is the important parameter. But whenever I am saying specific power, in that case, energy per time, okay, it should be very high. And per time means the time should be very short. In very short time, battery should be able to produce very high energy. Specific power is important in the reduction of battery weight, especially in the high power demand applications such as HEVs. So designing specific power source is also another matter of study. Specific power of a chemical battery depends mostly on the battery's internal resistance. So I'm going to show you in next few slides what is the mathematical model or what is the electrical model, that means which will be requiring some resistor, some capacitor and all those things. So internal resistance of the source should be as less as possible. If internal resistance is less at that time, inside the battery the loss will be less. In that case, the battery will become a high power source. So with the battery model shown left, the maximum power that the battery can supply to the load is given by. So VO is the battery, R int is the internal resistance, RC is another resistance, and R load. So this is what is the motor. R load is nothing but the motor. And what is RC, what is R int, it is given in the consequent slide we will see. So this, for specific high specific power source, this internal resistance should be as less as possible, though it is shown variable, but for battery it is not variable. Okay, so the maximum power that can be supplied to the load is, so power is nothing but voltage by current. Now current is nothing but voltage by resistance. Sorry, power is equal to voltage into current, and current is nothing but voltage by resistance. So you are finding VO divided by R int plus RC plus R load. Okay, here we are not showing R int, because you know the maximum power transfer theorem. What does maximum power transfer theorem says? That the internal resistance should be equal to external resistance. So what is RC? RC is the conductor resistance, ohmic resistance, and R int is the electrical resistance caused by the chemical reaction. Okay, so R int is the battery resistance. Okay, that is the internal resistance which is caused by the chemical reaction. RC is the conductor resistance. Whatever wires and all those things are connected, that is having a resistance, is value of RC is very small actually. That is actually given by RC. And we know as per maximum power transfer theorem that R load, if that is equal to RC plus R int, in that case maximum power will be transferred from the source to the load. This we know. So if R load is equal to RC plus R int, then maximum power will be transferred from the source to the load. And what is the formula for maximum power transfer? That is nothing but P peak is equal to VO. VO is nothing but the supply voltage divided by either load resistance or R in plus RC. And we know this condition, that for maximum power transfer theorem, R load should be equal to R in plus RC. So hence, either you could write VO square divided by 4 into R load square, 4 into R load, not square. Okay, so VO square divided by 4 into RC plus Rint, or VO square divided by 4 into R load. Because we know for maximum power transfer theorem, RC plus Rint should be equal to R load for maximum power to be transferred from source to the load. So there are three parameters in this circuit, three resistance parameters. One is internal resistance, which is the caused by chemical reaction, and this variable because rate of chemical reaction if more. So if the battery is under high heat, at that time rate of chemical reaction will be more. At that time the Rint also will increase. RC is nothing but the conductor resistance. So this battery is connected to the load by means of many different wires. So total resistance of that RC value is very small, and R load is nothing but motor, because your EV actually is run by a motor, and that motor is nothing but the load. And if I'm saying it's DC series motor, in that case the series resistance and the field resistance, okay, armature resistance plus field resistance together, this will be actually equal to R load. If it is shunt motor, in that case the calculation will be different, but generally DC series motor is used in EV for less than 2 kilowatt hour power. Okay, so that is what it is. So I think this slide and previous slide, it is very important, so please prepare these two slides properly. Previous slide is nothing but for the specific power, and this slide is for the specific this slide is actually for the specific power. Previous slide was actually specific energy, and this is actually battery circuit model. The left side, whatever you're finding, there is an internal model of the battery circuit. Okay, we will go to the next slide, and this is nothing but about specific power. So they are giving the same formula. So internal resistance Rint represents the voltage drop delta V, which is associated with battery current. The voltage drop delta V in the load actually termed as over potential in battery. So all those things you can check. P peak is equal to VO square divided by 4 into RC plus Rint. Somebody would say that VO square divided by 4 into R load, all those things. Delta VC. Okay, how to find the delta VC? Delta VA is nothing but A plus B log I, where A plus B are the model constants. So which model actually we are calling about? So here, accurate determination of battery resistance or voltage drop by analysis is difficult and is usually obtained by a measurement. So here, this graph again, if you remember, it was shown to you. So below, okay. So at the top, you are finding the voltage delta V termed as the over potential in battery terminology. So inside battery, there is actually some kind of voltage drop, which is called as over potential. It includes two components. First one is caused by the reaction activity delta VA, and second one is caused by the electrolyte concentration delta Vc. So inside the battery there are actually two voltage drops. One is delta Va, another is delta Vc. Delta V A is given by A plus B log I, where A and B are the model constants. I'm going to show you the model shortly. And what is meant by delta Vc? This is RT by NF, ln 1 minus 1 by IL. So R is the gas constant, T is the absolute temperature, N is the number of electrodes, F is the Faraday's constant, and IL is the limit current. All this slide things, it is not it will not be asked in the exam, but just for your knowledge, you remember that what are the different drops that occurs inside the battery. So inside battery also there comes some voltage drop. So if the battery is actually giving out 2.03 volt, maybe inside the battery it is zero point 0.2 or zero point 0.3 volt drop is there. So actually it is generating maybe 2.25, but removing the drop we are actually getting 2.05. So that zero point 0.2 volt drop is given by delta Va and delta Vc. They are all internal parameters and they are mainly chemical parameters. Okay. Hence, accurate determination of battery resistance or voltage drop by analysis is difficult and is usually obtained by measurements. So you can find out. So battery internal resistance ideally should be zero. But how much is the battery resistance at any time? And as the battery ages, as it becomes older, the battery internal resistance increases. Okay, as it is under a huge amount of heat, the battery internal resistance increases. The battery internal voltage drop across the battery increases with an increase in the discharging current. Again, another thing we are finding, so more is the charging discharging cycle, and you will be finding that slowly, gradually, the internal resistance of the battery will increase. So decreasing the storage energy. So as the battery gets older, its resistance increases and energy storage decreases. Discharge graph of different lead acid battery of different discharge is shown here. Again, I'm telling you that this kind of graph will be asked in your IA2. I will call it different discharge graph. Okay, so discharge, you can find out if the discharge current is 10 ampere, you are starting actually from 2.03 volt. Understanding this graph is very important. So this x-axis is capacity, ampere hour, y-axis is cell voltage mainly starting cell voltage. So previously day also this graph I had explained. Again I am explaining it today. That is, if I am asking lower current, you will be getting initial voltage high. So for lead acid battery, it is 2.03 volt. If I am asking for 10 ampere current, in that case, we can start from 2.03 volt. But if suddenly I am asking for too much current means around 100 ampere. In that case, we will be finding that this is not starting from 2.03, but this will be starting from 1.85. So this is one thing you have to notice, that too much load if you are putting on the battery is going to curve down. It is saying that I'm not able to give you that much high voltage. In that case, we'll be starting from 1.85. Somebody is asking for 20 ampere, it will start from 2.01 instead of 2.03. Likewise, so if you're asking for too much of current from the battery, its voltage rating, initial voltage rating will reduce. And you are finding that it is giving you current, quite constant current. I am talking about this 10 ampere, almost up to 80 hours. Almost up to 80 hours, it is giving you quite a constant current. And after 80 hours, suddenly there is a drop. Okay, so if it is capacity ampere hour, that means almost up to 80 ampere hour, it is giving you 10. That means after till 8 hours, it will be giving you quite good rating of output. Okay, so this is 10 multiplied by 8, that is 80. So up to 80 ampere hour. 80 ampere hour means 80 hour with 10 ampere capacity. If I am saying 20 capacity, 20 ampere, so you will be finding that this is giving you less. So this is almost up to 4 or 5. It is 4 or 5 hours, it is giving you good current. After that, it is reducing like that. So this graph, that is capacity versus cell voltage graph, you should remember. And you have to always remember that if you are charging the battery too much, if you are pushing the battery too much, you are not going to get the required voltage, because from lead acid battery we want to get 2.03 volt, and that can only happen if you are getting 10 to 15 ampere. Specific power table, as we have found specific energy table. So the specific energy table, specific power table, these will not be asked in the exam, but just for your knowledge and just for the comparison, you should be having all this thing with you. So you are finding that it is an acidic aqueous solution, lead acid battery. Specific energy, that is watt hour per kg, is 35 to 50. Peak power voltage per kg is 150 to 400. Energy efficiency greater than 80. Cycle life means how many times you can do charging discharging. So almost up to 1000 it is going. So it is saying 500 to 1000, that is mean and max value. Self discharging per percentage per 48 hours. That means if you just keep the battery idle, how much percentage of the battery voltage will reduce in 2 days, that is 48 hours. And cost US dollar, it was 120 to 150 per kilowatt hour. So if you are getting a bigger battery, in that case it will be higher kilowatt hour. And I'm telling you that this is data for 2000, year 2000. Okay, nowadays things have changed quite a lot, so you have to find the cost in a new way. So this parameters, I'm asking you all, those who are joining this field of EV, you should remember all these parameters. So these parameters I can ask you in the exam. That is, if I want to check a battery, what are parameters should I be looking for? Or if I'm going to purchase a battery, what are parameters should I be looking for? So one very important parameter, specific energy. So depending on its weight, how much watt hour it will give. Peak power, depending on its weight or kg, how much voltage it will give. What is the energy efficiency? So you are finding that below, that is molten salt batteries, they are giving you efficiency almost 80 to 80%. And again, you are finding lithium ion battery, it is giving you more than 95% efficiency. So we have seen the most old battery, that is lead acid battery. Now we are going to see lithium ion battery. The specific energy is 80 to 130. For lead acid, it is 35 to 50. Now it has increased drastically. 80 to 130 means 80 is minimum, 130 is maximum. Peak power, it previously it was 150 to 400. Now it is 200 to 300. So this is more specific. Range is smaller, but range is quite big. So previous low was 150, now it is 200. Previous high was 400, now it is 300. Efficiency is a very important thing for lithium ion battery. It is greater than 95%. For lead acid, it was greater than 80%. Cycle life 1000 plus. Cycle means charging, discharging, charging. So one discharge then charge, this is called a cycle. Okay, or one charge first and discharge next, it is called a cycle. So cycle life is 1000 plus. Okay, whereas you can see that for lead acid battery the cycle life is 500 to 1000. So this kind of comparison I can ask. So one question you can write down in this case from this slide number 8, that is compare the parameters of lead acid battery and lithium ion battery. So this is one question I can ask, though I told you that I will not be asking, but this one question you can prepare and it can be asked for a 5 marks with some more additive questions. So only 5 6 details you have to remember with the parameters: specific energy, peak power, energy efficiency, cycle life, self discharge, and cost. So cost is also quite high but not very high. Okay, with respect to 150 it is only you can say there is 25%, right? So only 25% increase, all 25 to 30% increase it is there. So this is a very important slide, that is specific power related details are given in this slide. And after that what we are finding is the table shows the status of battery system potentially available for EV. So what are the different battery system? Mainly previously it was lead acid battery, then nickel iron had come, and then presently it is lithium ion. Although specific energies are high in advanced batteries, but specific powers must improve. Major manufacturers of lithium cadmium battery. So this is another important contender. Previously it was nickel cadmium battery is just below the lead acid battery. You can check, and it is having cost quite high, but it is having cycle time 800 and efficiency is around 75. So major manufacturers of nickel cadmium batteries for EV and HEV applications. So these are the two companies, if you remember. One is SAFT, another is Vata. Okay, so SAFT and Vata are two companies which are actually too much into this battery technology. So SAFT and Vata, they had produced nickel cadmium battery for HEV application. About 300 watt per kg might be the optimistic estimate. However, SAFT had reported its lithium ion battery has capacity 85 watt hour per kg, specific power of 1350 watt per kg. So these are the units. What is the unit of specific power? You can write down. Specific power unit is watt per kg, and specific energy unit is watt hour per kg. Okay, so I'm repeating again the important thing. Specific energy unit is watt hour per kg, and specific power unit is watt per kg. Okay, because if you are multiplying energy, if you are dividing energy with time, you are getting power. So whenever you are dividing watt hour per kg by time, so this hour thing goes. In that case, what remains is only watt per kg. So these two things you should remember. That is, specific power unit is watt per kg, specific energy unit is watt hour per kg. And this is one specification, that is SAFT has reported lithium ion high power for HEV application, which gives specific energy of 85 watt hour per kg but specific power of 1350 watt per kg. It's high energy batteries for EV application with about 150 and 420 watt per kg. So whenever I'm saying watt per kg means its specific power. At 80% state of discharge, 150 ampere current and 30 seconds. Okay, so whenever it is 420 watt per kg, that is another battery specification they are given. 150, okay, 150 application with about 150, it's high energy batteries for EV application about 150 and 420 watt per kg. So 150 watt per kg and 420 watt per kg at 80% discharge, and 150 ampere current and 30 seconds. So these are the discharge time and this is the discharge current. So these were the main things actually in this slide or in this PPT. Next, what we are going to see is energy efficiency. This is another very important thing, but there are a lot of very critical kind of definitions and all those things are there, because there are two types of efficiencies. One is called as a charging efficiency, another is called as a discharging efficiency. And you are finding the graph in the right side. You are finding that this is a typical battery charge and discharge efficiency. So you are finding that this graph, which is starting from the left side and going up in the right side, this is the discharge graph. Okay, and whatever graph you are finding falling down, this is the charge graph. Okay, you are finding this is a charge graph. So as the battery is charging, its efficiency is actually reducing. That you have to find. And at very center, that means whenever the state of charge is 0.5, I think I have given you the definition of state of charge. Okay, it was that SOC T is equal to SOC T minus 1 plus some time parameter and all those things are there. So state of charge means 0.5 means 50% charge is remaining, and you are finding that both for charging and discharging, whenever 50% charge is remaining, at the time efficiency of the charging and discharging process is highest. So whenever I'm keeping the battery 50% charged or 50% discharged, you'll be finding that at that time charging or discharging happens at very faster rate. Okay, if the battery is fully charged, you are finding in this case right side. So this graph, whichever is falling, okay, whenever the state of charge was zero point 0.5, it was charging quite in a higher rate, but as the battery is getting fully charged, so this side it is fully charged, you are finding, because SOC is going almost towards zero point 0.8. So this graph you have to really understand properly. So as SOC is increasing, that means battery is getting fully charged, the charging rate, actually efficiency, it is actually reducing. So efficiency means how much power the battery is holding and how much energy you are giving. So whenever the state of charge is increasing, you are finding this case. At that time, you are giving more energy input, but not all of them are being held by the battery. Okay, so here the efficiency is decreased, you are finding. So this graph is very important. When SOC is increasing means battery is getting more and more charged. In that case, efficiency is reducing. What is meant by efficiency is reducing? More energy you are giving to the battery input, but battery is not able to hold too much of those energy. So efficiency is reducing. So that's what I told you. Whenever you are charging your mobile phone battery, always try to charge it in between 40% to 80%, or maybe 40% to 70%. Because above 70%, whenever you are trying to charge your mobile battery or any battery, you'll be finding that for each 1% increment in the charge, you have to input too much of energy. That means efficiency of the charging is reducing as battery is getting more and more SOC. So there is a contradictory fundamental, and this is difficult to understand. So this graph you have to understand very properly. Whenever the battery is discharging, just see this characteristic. Battery is discharging means initially this is discharging at a very slower rate. Initially this battery is discharging at a very slower rate, means it is not able to give more current at the output. Okay, in that case efficiency is very low. So in that case discharge, so at higher discharge, very high discharge, you are finding the battery efficiency is high. Whenever the battery is doing very high discharge, at that time you will be finding that battery efficiency is very high. What is meant by battery efficiency during discharge? It is how much charge you are giving to the other divided by how much charge the battery is having inside it. So charging efficiency and discharging efficiency definitions are reverse. Charging efficiency means how much charge is held by the battery divided by how much charge you are giving to the battery for charging. This is what is called as the charging efficiency. What is meant by discharging efficiency? Discharging efficiency is how much charge you are giving at the output, because efficiency is always output by input. Discharging efficiency is how much charge you are giving at the output divided by how much charge you have in you in the battery. So during discharge, battery is not charging. During discharge, battery has to give everything from itself. Whatever it has from here, it has to give out everything. So this discharge efficiency, and we are finding in both cases, that is when the efficiency is around 0.5, or sorry, not efficiency, SOC is around 0.5, at the time efficiency is maximum. Very important thing. So the energy of, so we are studying the last very important parameter, which is called as energy efficiency. So power losses during the battery charging and discharging appear in form of voltage loss. So the efficiency of the battery during discharging and charging is defined as, at any operating point, as the ratio of the cell operating voltage to the thermodynamic voltage. So thermodynamic voltage is nothing but which is generated by chemical reaction, and cell operating voltage is what you are measuring by the voltmeter. So that is eta is equal to V by V0 during discharging. So V by V0 means how much voltage you are generating at the terminal, and how much initial voltage the battery had. That is actually during discharging. This is the efficiency. Charging efficiency is V0 divided by V. V0 is how much is the battery voltage divided by how much is the charging voltage. So these two definitions you can remember from the slide number 9. Discharging efficiency is V by V0. V is nothing but what is the terminal voltage divided by how much voltage the battery has in itself. That is V0. And V is the terminal voltage. And eta, that is efficiency for charging, is how much voltage is getting stored at the battery. So what is the battery voltage divided by how much is the connected voltage at the battery input. So these are the two definitions. समझ के पढ़ो, then it will be easier. Terminal voltage as a function of the battery current and energy stored in it, that is SOC, is lower in discharging and higher in charging. We are finding here discharge graph. So initially when the SOC is 0.2, 0.3, that means battery is almost discharged. In this case, efficiency is also less. When the efficiency increasing, for discharge, when the SOC is increasing. That means more you are inputting charge inside the battery, it can discharge better. So this way also you can remember. More you are pushing charge inside the battery, that is SOC is 0.3, 0.4, 0.5. SOC means state of charge. So state of charge is 0.5 means it is 50% charged. In that case, you can discharge also better. Okay, but greater than 0.5, greater than 50% SOC, you are finding that the battery efficiency is increasing, but it is getting saturated. Okay, and reverse is charging. So you are finding that is lower in discharging and higher in charging. In an electrical figure shows the efficiency of the lead acid battery during the discharge and charge. Battery is a high discharging efficiency with high SOC, you are finding right side, and battery is a high charging efficiency at low SOC. Okay, so in this case you are finding that the battery is already charged. Okay, in this case you are finding a very high efficiency. More is the battery charging, more is the SOC at the time its efficiency is actually decreasing. So the net cycle efficiency has a maximum in the middle. So if you add these two graphs, you are finding below. So this net cycle is nothing but the addition of these two. Okay, addition of these two. In that case, you are finding the net cycle efficiency has a maximum in the middle. Therefore, the battery operation control unit HEV should control the battery SOC in the middle range to enhance the operating efficiency and depress the temperature rise caused by the energy loss. High temperature would damage the battery. So if you are operating the battery too much in the low SOC range or too much in the high SOC range, in that case, you will be finding that at the high SOC range during charging, battery will get heated up very much. And in the lower SOC range, because of discharging, the battery will get heated up very much. But whenever you are keeping SOC at 0.5, at the time battery will not get heated up and it will be having very high efficiency. So that's why they are saying when SOC is in the middle range, then the operating efficiency is enhanced and it depresses the temperature rise caused by the energy loss. Because whenever I am saying efficiency is less, that means loss of energy is happening. So for discharge at the starting part, for charge at the higher part, higher SOC, efficiency is less means battery will get unnecessarily heated up. So always you should try to keep the SOC of the battery in between 0.5 to 0.7 range. In that case, you will be finding that battery is getting cooled off or battery is not getting too much heated up. Different battery technologies, though I have put it in the figure, but I will not be, or in the slides, I will not be asking it in the exam. Whatever part I will ask in the exam, I'll tell you. So first they are saying lead acid battery, successful commercial product. So this is a very widely accepted it was, and it was very widely used. But when the lithium ion battery has come in the market, at the time the days of lead acid batteries are gone. So question that can be asked from here, if you can write, it will be advantage and disadvantage of lead acid battery. So lead acid battery means we are using those PbSO4 and other things. Previously, I have given you the reaction of lead acid battery in the previous day. So you can find here there are different types of battery: lead acid, nickel based, such as nickel iron, nickel cadmium, nickel metal hydride, all those things. Lithium based batteries such as lithium polymer, lithium ion, like that. So it seems that cadmium based and lithium based batteries would be the major candidates for EVs and HEVs. What are the advantages of lead acid battery? It is low cost, mature technology, and relatively high power capability. Hence, they are attractive for application in HEVs, where high power is the first consideration. So, lead acid battery and high power batteries. Materials involved: lead oxide, sulfur acid, that is sulfuric acid, like that. Other rather low cost when compared with their more advantageous counterparts. What are the disadvantages? Energy density is low. It is said that it's a high power capability, but energy density is low. That means lead acid battery is a better contender for HEVs, but not for EVs. That you have to understand. Mostly because of the high molecular weight of the lead, energy density is low. That means lead is very weighty. And we have seen that for high energy density, we need a less weighty substance. So lead is very high in weight That's why it cannot be a good contender for high energy battery source. The temperature characteristics are poor. Below 10 degrees centigrade, specific power and specific energy are greatly reduced. Aspect This aspect severely limits the application of this battery for the traction of vehicle operated in cold climates. So in cold climates, you cannot use lead acid battery. So in hot countries or medium kind of like India, this kind of countries, you can use lead acid battery for HEV, not for EV. More problems with lead acid batteries. So this you can just go through. The presence of highly corrosive H2SO4 is a potential safety hazard. So if the car is facing an accident, in that case, this H2SO4 can spill on the passengers or the drivers. That can cause unnecessary accident. Hydrogen released by the self-discharge reaction is another potential danger, since hydrogen is extremely flammable. Okay, so whatever reactions we have seen in case of lead as the electrolyte, hydrogen will be you can say discharged by some of the electrodes, and hydrogen itself is self-flammable, so that can be like a time bomb. Hydrogen emission is also a problem for hermetically sealed batteries. What is meant by hermetically sealed batteries? Previous age, the batteries we had to add water in old batteries. In hermetically sealed battery, we don't need to add water. Okay, in hermetically sealed battery, they are sealed and they themselves run themselves. They don't require externally added water in that. Indeed, to provide a good level of protection against acid spills, it is necessary to seal the battery, therefore trapping the parasitic gases in its casing. So a lot of gases actually are getting trapped inside this hermetically sealed battery. Sometimes they bulge out. So battery sometimes becomes bulging out and sometimes they burst. As a result, pressure buildup. So next line they are saying like that. The pressure buildup inside the battery, causing swelling and mechanical constraints and causing casing and the sealing. The lead in the electrodes in an environmental problem. So lead is actually a poisonous element. So lead acid battery is containing a lot of lead, and actually that is creating some kind of poisonous problem. And if there is an accident, this lead and the related acid might actually do damage to the health of the passenger and the driver. Advancements in lead acid batteries. So there are some companies which are named, and there are many advancements that has happened in lead acid batteries. You can go through. Definitely it will not be asked in the exam, but yes, we can ask about the advantage, not advantage, yes, the advantage and disadvantage of lead acid battery. This can be one question. More disadvantage, yes, because of this we have shifted to lithium ion battery. Second is nickel based batteries, NIFE. This is the oldest technology and used for forklift trucks, mine locomotives, shuttle vehicles, and all those things. So just you remember and what are the applications that which is there. You don't have to remember all the details stage by stage. They are just given. You can do the power and specific energy comparison, and you can remember where is the application. So this is NICD. NICD is another very important thing. It is gives high specific power, almost 220 watt per kg, long life cycle up to 2000 cycles, high tolerance of electrical and mechanical abuse. That means you can rough use this nickel cadmium battery. A small voltage drop over a wide range of discharge current, rapid charge capability, all these things are there. But nickel cadmium battery is sturdy, that much you understand. Nickel based batteries, NIMH, okay, it came in the market in 1992, and you are finding its specific power is 200 to 300 watt per kg, specific energy 70 to 95 watt hour per kg, and all those things. Okay, so these are the three nickel based batteries. This one will be important. Okay, so this slide 16, 17, 18, lithium based batteries. Lithium P is used, but it is written here, thin solid polymer electrolyte is used. SP offers the merits of improved safety and flexibility in design. So electrolyte, so you are finding that there are two types of lithium battery. One is lithium phosphorus, one is lithium ion. So lithium is the lightest of all metals and possesses very interesting characteristic from an electrochemical point of view. Indeed, it allows a very high electrodynamic voltage, which results in very high specific energy and very high specific power. So this is the main reason of lithium, because lithium is very lightweight. That means we can pack the battery with huge amount of reactants. Okay, that's why it is producing very high specific energy, very high specific power, all those things. There are two major technologies of lithium based batteries, LIP and LI. LIP is lithium, and LII it is I think it is okay, like that. So P is explained in this slide. It is a lot of chemical things are given here. Don't worry about that. Only thing you have to understand is LiP is, it is having a solid polymer electrolyte. SP is used. This is good from safety point of view. It operates at nominal voltage of 3 volt. That means one voltage, one battery gives you 3 volt. Specific energy is 125. Specific power is 15 watt per kg. Corresponding advantages are low discharge rate, only 0.5% per month. Previously, it was 0.6% per month for lead acid. For lithium P, LiP, it is 0.5% per month. Capability of fabrication in a wide variety of shapes and sizes. It has drawback of relatively weak low temperature performance due to the temperature dependence of its ionic conductivity. That is, if temperature is more at that time, this battery generates high internal resistance. Higher is the internal resistance, lower will be the efficiency. That is P battery. LiI battery, main contender our electric vehicles. The first announcement of LiI battery rise with amazing rechargeable battery of the future. Nowadays, they are talking actually about the sodium batteries. Okay, sodium batteries are also used very widely, and they are saying that next generation will be for sodium battery. So, although still in development, they are talking actually about year 2000, not now. Battery has already gained acceptance for EV and HEV application. So, lithium ion can give you both for high specific energy and specific power. Lithium-ion battery uses a lithiated carbon intercalation material LiXC for the negative electrode, and LiXC is used as positive electrode, LiXC, and a liquid organic solution or a solid polymer for the electrolyte. So acids and all those things are not used here. That's why this is also safe from passenger point of view. On discharge, Li ions are released. Previously, hydrogen was getting released. Here, lithium ions are released from negative, and they migrate via the electrolyte, and they are taken up by the positive electrode. On charge, the process is reverse. The positive electrode material have the advantage of stability in air, high voltage, reversibility for the lithium intercalation reaction, etc. So, little bit of understanding of lithium-ion battery you can find from this slide, and they are giving some specific specifications of 4 volt specific energy, 12 watt per kg, and energy density 200 watt hour per liter, specific power 200 watt per kg. Cobalt based battery has this. So some of the details you might remember. Actually, I have shown you 2 charts initially. From there you can find out what specifications of lithium ion battery, lithium P battery, all these things. And these 2 companies you should remember, Saft and Varta. Their design and all other things, their products. Hitachi is also there, Saft is there, Panasonic, Sony. But I'll tell you, all these companies they are talking about in 90s up to 2000. Latest, many more companies have come because a lot of EV things have come. Many more companies have come, so you should be careful, and you should find some new companies which are actually in the market, which are generating batteries. Next, I will talk about, sorry, just one sec. So do not much worry about the construction and other thing, because anyways the questions will be given about what we want to do. So this lithium ion battery, I think this slide we have seen. Next, there is another slide. This is the last slide, slide number 18. We will stop with this. It is saying that the nickel-based lithium-ion battery has nominal voltage of 4 volt. So this you should remember. Nickel-based lithium-ion battery has nominal voltage of 4 volt. Tesla, what I studied, it was having 3 volt batteries. 3 volt batteries connected in series and parallel. And Saft, GS, Panasonic, Sony, they are the companies who are in the battery technology. So with this, I will stop today's lecture. 7 minutes.